Yes, good evening. This is Benza Samuel, and I'm covering the second bit of the models, that is for the West classification system. So here with me, I'm going to be taking you through the binary and multi-class classification for West type detection, where for the models that I'm dealing with are to do with random forest, X-key boost, then for the neural network. The objective is majorly identifying the West types, which the nine classes, with focus that is mainly based on West detection. So looking at the project overview, we have the problem statement, where we have our data characterized of the 9 West classes, that is E-West, the cardboard, then the glass, metal, organic, then we also have paper, plastic, textile, that's then lastly we have trash. So there are 1,000 samples that we generated from the real statistics distributions. They are featured, all the features extracted from those images as mentioned. So when we look at the objectives, mainly it's based on binary classification, that is detecting E-West versus the non-E-West. Then the multi-class classification, that is majorly classifying the 9 West types. When you look at the key features, we have the aspect ratio, the brightness, contrast, edge density, entropy, image dimensions, file size. Majorly, that is what we are looking at for the key features. Then when we look at the data pipeline architecture, we have the data generation and processing flow, where we have the statistical distributions, that is for the data sets, which lead us to the synthetic data generator that takes us to the feature engineering bit of the work. So after the feature engineering, we get to the feature scaling, then we train and test. That's where we split to 80 to 20. Yeah, then we model the training. So here we normally look at 3 algorithms. So looking at the feature engineering architecture, the engineered features are 18 in total, where we have 9 being base features, where we have the aspect ratio, the blur, then the brightness, contrast, edge density, entropy, width, height, file size, that is covering up the base features. Then the derived features are 5, where we have the aspect ratio, that is for the squared, which is a nonlinear relationship. Then we have the brightness contrast ratio, that is for the lighting versus the texture. Then edge entropy interaction, majorly taking up the structure and complexity. Then we have the blur edge interaction, that is for motion blur impact. Then we have texture complexity, that is taking up the entropy over the edge density combined together with the blur. So when we look at the categorical features, here we look at the resolution category where we have low, medium, high, very high, where they lead us to one not encoded feature. So when we look at the binary classification model architecture, first of all, we look at the problem that we are having at hand, that is the e-waste detection. So the target variables, that is for our e-waste detection problem, we have the e-waste, then the non-e-waste. Those are major points of concern. Then here we look at the three parallel models, that is for the input features, as earlier mentioned. If we are to go back a bit, where we have the engineered features, which were 18 in total, and now we're now looking at the models themselves. So when we have these input features, which are 18 in number, as earlier mentioned, we have them taken into random forest, that is for the baseline, the XGBoost, that is for the enhanced, and neural network, that is majorly for the MLP. So, so when we look at them in detail, we have them taken in for the trees. We have 100, that is for the random forest. Then for the maximum depth, it is always by default. So for the XGBoost, that is for the trees, we have 100. Then the maximum depth is 6. So when we come to neural network, that one is always 100, then leading us to around maybe 50. So the activation as seen. So when you look at the output, after looking at these features that are modeled, so our output is always the e-waste with a probability score. Yeah, probably with that probability score. So when you look at the random forest architecture, that is for the binary. Here we look at the ensemble of decision trees, where we have the training data, which is split into 3. That is for the type 1, type 2, then up to infinity, where we have our last, since we had the workspace, it took us up to 100. So in between, there are very many models that are being trained, but majorly we look at these as samples. So after these, first, second, up to the 100th tree being modeled, in the due, as we try training the data, we end up having the probability averaging to the final prediction. So for the key parameters, we have the estimators, which as I earlier mentioned, we estimated our workspace, that is for the data training, to be 100. Then we did bootstrap sampling, then feature randomization, that is specifically for the key parameters that we deployed. So for the XGBoost architecture, that is still on binary, we have the gradient boosted tree, the gradient boosted decision trees, where we look at the code starting from the initialization, where we start with the constant prediction with this formula as it appears, because according to my testing that I did on the waste detection, looking at the data sets that I have into consideration. So after this initialization, we have the iterative boosting, that is for where we have for m equal to 1 up to 100 for the sample spaces that for the sample spaces that I personally chose to take on, that is from the first up to the 100th. So when we look at the computation, as looked at the formula provided on the previous slide, when we compute, this is the algorithm that is followed towards the testing and training of the models. So here at the end of it all, we have the final model, that is fx, for the summation of the n, then for the maximum bit of the sample spaces that we are supposed to be testing. So for the regularization, we have our L1 over the L2, that is on the leaf weights, the shrinkage, and then so the column subsampling. Then for the neural network architecture, that is on binary MLP, that is the multi-layer perception structure. So here we still have the input layer leading us to the first hidden layer, then to the second. Then later we proceed on to the output layer, where we have one neuron. Then on activation, we have a sigmoid. Then for the output, it's either a 0 or a 1. That is for the output in the for the e-waste. That is as for our point of concern. Then when we look at the training, first we have the optimizer, the maximum interactions, or maybe we can call them iterations, any of them. Then we have the early stopping, that is with 10% validation split. Then we have the loss, that is binary cross entropy, where we normally have the loss occurring. Then for the multi-class architecture, that is for the multi-class classification architecture, we have the target classes as e-waste, cardboard, then glass, metal, organic, that is paper, plastic, textile. Then we also have trash. Here we look at them in terms of for the component, the output layer, the output activation, the loss function, then the evaluation. So for the component, we majorly have binary and multi-class. Then for output layer, it is in either one neuron or 9 neurons. Then for the output activation, we have a sigmoid, then We also have softmax. Then when we come to the loss function, we have binary cross entropy. Then we also have categorical cross entropy. When we come to evaluation, that is for the last bit of it, we always have the accuracy, that is always F1, which represents for that represents the binary. Then we also have the per class matrix. When we come to the neural architecture, that is for the multi-class, we look at the X gibbous, that is for the multi-class, which here we present there is an illustration that is giving us the clear picture on the multi-class extension, that is with the softmax, where we have the X gibbous, that is for the multi-class, with the objective, and inside it we look at the class for each class, where we have k equal to 1, taking us up to 9. So when we train separate tree ensemble, that is for the class k, using the one versus the rest approach with softmax, it finally gives us the final prediction that results from training the model. So we look at the parameters still as earlier mentioned. Here we have the estimators, the n estimators, where we have 150, the maximum depth, that is 8. Then the learning rate. The learning rate is 0.1. Then the metric, it's always m then log the loss that we have experienced during the training of the model. So when we look at the model training pipeline, that is majorly looking at the complete training workflow. Here we have data preparation, that is in first step, where we have generating the synthetic data from the statistical distributions. Then we engineer the 18 features, that is for the 18 features that we have for the engineered features. Then we look at the scale features, that is using the standard scalar. Then the split percentage, that is 80% for the split, then 20% for the training. Then the test itself is stratified as we look at the model. So when we come to model training phase, here we majorly have the 5-fold cross-validation, where we train the model. We first get the first score, the second score, that will eventually lead us to the final score, where we have the mean multiplied by 2, by the standard deviation, then all multiplied by 2 to get us the final score. So when we get to the model evaluation, that is according to the training workflow, we look at the test set accuracy, then classification report, that is mainly looking at the precision, the recall, then the F1. Then we also have the confusion matrix that is also put in consideration, that is for the model evaluation. Then we have the feature importance, that is for the tree-based models. So when we look at the feature importance mechanism, first consider the random forest feature importance, where we have for each tree in the forest, that is for each feature, we gave it a variable of f. So that importance, when we look at that importance, that is for the variable that we use, that is f, it should give us to a total, it should lead us to a total reduction in the gene impurity. That is for at all the nodes splitting on the variable, that is the variable f that we're using for each tree that is in the forest. Then when we come to the XGBoost, that is for the XGBoost features, it also holds three types. That is the weight that represents the number of times the feature is used for splitting. Then we have also the feature, the XGBoost feature importance type, which is the gain, where we have the average information gain when the feature is used, then the cover bit of the type, where we have the average coverage of the feature splits. So implementation in the code, just as I earlier mentioned, during the implementation of the code, we majorly look at the model, the feature importances, where we have the importances being equated to the model, that is being multiplied by the feature importances. And we also have the indices that are equated to the NP, then also multiplied by the importances, that is for the AgSort function. So yeah, this other bit of the code is majorly for the visualization, that is for the plot, where we have a bar graph that represents the visualization of the models that are being trained. So when we come and look at the neural network training dynamics, still we have the MLP optimization, MLP optimization process, where we look at the forward propagation, then we have the back propagation, and that is optimization. So when we come and look at the time of early stopping, that is for the model being trained, we majorly look at the monitor validation loss. Then we stop if no improvement for the 10. If there is no improvement, then we also restore the best weights, that is at early stopping. So we look at the model evaluation architecture, that is for the performance metric computation, where we have a test set, which is to 20% of the data, where we do model prediction in accuracy, that is for the accuracy score, then for the confusion matrix, then we also give a classification report, that is for the precision, which eventually leads us to the cross-validation, where we have the scores for the fivefold, giving us the mean, the mean that is for the formula for obtaining the formula for obtaining uh, the formula that we used for obtaining the scores, that is the scores that are involved in the training. So that method was earlier mentioned in the previous slides, where we had our mean being multiplied by the standard deviation, then multiplied by 2 to give us the scores as per the training of the models. Then we come to the prediction pipeline architecture, where we have the inference system design, that is for the input features, where we have the aspect ratio, the blur, the brightness, the contrast, and the others, totaling up to the 9 that we had in first place. Then that leads us to the feature engineering, where we have the aspect ratio, the aspect ratio squared, then brightness, contrast ratio, the edge entropy interaction, the blur, edge density interaction, the texture complexity, the resolution category. That is all in the feature engineering. So when we come, but in between the feature engineered features and the models themselves, we have to deploy a standard scaler that is for the feature, where we eventually get a binary model that is for the best performer with a multi-class model, where for the binary model, we have our output as the west, that is for the e-west, with a probability of either 0 or 1, and for the output being the predicted class confidence for all the class probabilities. So in summary, we have the architectural advantages that are involved in this architecture, that are used in training these models. We have the random forest. Then we also look at the model itself. Then the XGBoost. Then the neural network. So when we look at these, we normally look at the strength. That is for the model. Then we also look at the use case that is involved in the model. Then for the random forest, that is, we first take into consideration the baseline, that is which is interpretable, that handles the non-linearity. Then we also look at the benchmark comparison. Then for the XGBoost, it majorly looks at the regularized boosting that handles imbalance and the feature importance. Then it also looks at the primary classifier. Then when we look at the neural network, it captures the complex interaction, that is also for the flexible architecture. Then it also looks at the pattern discovery. So when we look at the key features that are involved in the architecture, we look at feature engineering layer, that is for the domain-specific transformations. Then we look at the dual classification, that is binary put together with the multi-class. Then we have the cross-validation framework that normally puts up a robust performance estimation. Then we have the standardized preprocessing, that is for the consistent feature scaling. Then lastly, in these features behind the architecture, we have the model persistence, which puts on the model ready for deployment. Then we shall be having our next steps, which are hyperparameter optimization, real image feature extraction, and then ensemble for all the three models, then deployment as the REST API. So with this, I come to a conclusion of my presentation. That is for the models under the class classification system, majorly looking at the model architecture that is involved in the e-waste detection.